Good morning, ladies and gentlemen. First, I would like to thank the organizer for giving us the opportunity to present our work in this important conference. My name is Anselmo Tabares. I am a permanent professor and researcher of the Universidad del Valle in Cali, Colombia. And today I will present this work carried out in our group of physical metallurgy and phase transitions theory. As we see in the title, today I will show you an optimized route for the fabrication of manganese, aluminum, carbon, permanent magnets by arc melting. Here I present the outline of my talk. First, I will present the motivation of this work regarding the importance of the permanent magnets for current and future technological application, especially those magnets which are free of rare earth elements, like the ferromagnetic manganese, aluminum, carbon. Then I will describe the fabrication process followed to synthesize the manganese, aluminum, carbon permanent magnets by arc melting. Here I will focus the discussion on the thermal treatment for the synthesis of this alloy, where we have proposed an optimized route. Afterwards, I will pass to present the crystal phases, magnetic and magnetic imaging characterizations of the samples under study. And I will finish my talk by summarizing the main conclusion of this work. During the past century, intensive research into hard magnetic materials led to an increase in the development of permanent magnets. They are essential in the everyday technologies, including the domestic consumption, energy conversion, transportation, and military weapons systems and electrical motors, or for in the main use of the wind generators. However, as we see in this graph of the maximum product or energy product, which is the figure of merit used to value the energy stored in this kind of materials, high-performance magnets are totally dependent on rare earth elements like neodymium or dysprosium or terbium, which are scarce and expensive due to rare earth crisis that started in the beginning of the past decade. So, they are considered critical raw materials. This situation makes the development of rare earth-free permanent magnets an urgent priority, posing a major scientific and technological challenge. A rare earth-free alloy to consider for permanent magnets application is the face-centered tetragonal structure of the near equiatomic manganese aluminum alloy, stabilized by a very low concentration of carbon between 1 and 2%. This alloy is called tau manganese aluminum carbon alloy. This alloy exhibits good permanent magnet properties, such as high anisotropy, a relatively high saturation magnetization, and a moderate high Curie temperature. Besides, being a low-cost materials. Thus, in the last 10 years, several works have been carried out aimed to establish the best procedure to obtain the tau phase of this alloy, to then improve its magnetic performance. Here we can see the binary phase diagram of manganese aluminum alloys. Typically, the tau manganese phase is obtained from the quenched hexagonal epsilon phase, which is then annealed at a temperature between 450 and 700 Celsius degrees. Thus, the metastable nature of the tau phase results of the transformation of a disordered hexagonal epsilon phase quenched at room temperature. However, in this crystal transformation, some equilibrium phases as beta manganese and gamma 2 aluminum 8 manganese 5 can appear and could deteriorate the magnetic properties of the ferromagnetic alloy. There are various techniques for the production of tau manganese aluminum carbon: hot extrusion, mechanical alloy, melt spinning, gas atomization, and arc melting. We are interested in to use this technique for the production of our samples. Hong-Jian described a thermal process for the synthesis of the epsilon phase. After the solution treatment finish, the alloy is quenched in water to retain the epsilon phase at room temperature, and the room temperature epsilon phase is annealed for several minutes at a temperature that is that remain in a value that varies in between 500 and 700 Celsius degrees. With this, to induce the epsilon 2 tau phase transformation. Now, in this work, we propose variation in the solution treatment. With this variation, first, we directly introduce the as-cast alloy to the furnace when the temperature was 1200 degrees, which is higher than the temperature than those previously used. The alloy was kept at this temperature for 4 hours to then reduce it 1 1100 Celsius degrees and kept it for a long time, in this case for 48 hours, to finally quench the sample in water at room temperature. The annealing treatment was the same as the first case. As we will see next, this variation allows getting optimized tau manganese aluminum carbon alloys. Now I will pass to present the main results of this work. Here I show the Xray diffractograms of the resulting manganese aluminum carbon alloy after following two different solution treatment routes. When we followed the route 1, the resulting manganese aluminum carbon alloy is a solid heterogeneous mixture that has three different phases: epsilon phase, which is the majority phase, together with this aluminum rich phase and a few amount of tau phase. The route 2 achieved production of a virtually pure epsilon phase according to Rydberg refinement that is not shown here. Thus, we found the two-step solution treatment favors the formation of a virtually pure epsilon manganese aluminum carbon alloy at room temperature. Here I present Xray diffraction results for the alloys after making the annealing treatment to induce the epsilon tau transformation. The epsilon phase-based alloy obtained by following route 1 produces a solid heterogeneous mixture alloy where the majoritarian phase, around 90%, is the expected tau manganese aluminum. This is the tau manganese aluminum. And the presence in this case of aluminum 6 manganese and beta manganese phases. For the epsilon phase-based alloy obtained by following route 2, where the pure epsilon manganese aluminum carbon is totally transformed in the tau manganese aluminum phase. Tau manganese aluminum carbon phase, without the presence of secondary phases. Thus, the high purity of the epsilon manganese aluminum carbon permits to synthesize a pure tau manganese aluminum alloy. Here I present the studious loops obtained for the two types of tau manganese aluminum based alloys for route 1 and route 2. We clearly see how the relevant magnetic parameters of pure manganese aluminum alloy, the tau phase, are better than the formed by solid heterogeneous mixture with 91% of the tau manganese aluminum carbon phase. The pure one has magnetization at the external field of 2 Tesla of around 100 ampere square meter per kilogram, a remanence magnetization of around 41 ampere square meter per kilogram, and a coercive field of 0.2 Tesla. The pure tau manganese aluminum alloy presents the best magnetic parameters. Comparing these results with those obtained by Hongjin, we found that our tau manganese aluminum carbon has optimized magnetic parameters that are relevant to design the high-performance rare earth free permanent magnets. Finally, a local exploration of the microstructure of the pure tau manganese aluminum carbon alloy was performed by transmission electron microscopy. In this figure, it is presented a TEM image at intermediate magnification taken in a small region of the sample by our colleague Luis Alfredo Rodriguez. We see as our fabrication process produces a polycrystalline sample formed by micrometer grains of different sizes and irregular shapes. Just in the image, we can identify grains of hundreds of nanometers of lateral size and very large grains of tens of microns. Inside some grains, we observe stacking folds and crystal defects that has been probably created during the epsilon 2 manganese aluminum carbon transformation. In this figure, it is shown a Lorentz image taken in a region of the sample by making Lorentz microscopy at TEM-based technique able to image magnetic contrasts of ferromagnetic materials. In this image, the bright and dark contrasts are produced by magnetic domains wall formed inside of the grains. As we see in this image, domain walls are formed inside all the grains, so that we could conclude all grains have the tau phase of the alloy. More Lorentz images were taken in other regions of the sample, and all the grains showed magnetic contrasts. It means that until now we could not detect the presence of micro or nano-sized grains of the epsilon phase or other non-ferromagnetic secondary phases. Here I present the main conclusions of this work. We produce tau manganese aluminum carbon alloys by a melting method where the most relevant permanent magnet parameter has been optimized. A two-step solution treatment allowed to produce a pure epsilon manganese aluminum carbon alloy at room temperature, and the annealing treatment in pure epsilon manganese aluminum carbon alloy achieved its total transformation to the tau manganese aluminum phase. This is the main conclusion in our work. Thanks for your attention.